Thanks for giving me this opportunity to share what my collaborators and I have thought about on this question. Unfortunately, I'm not able to attend in person. So I apologize if what I'm going to say overlaps with what have been said or discussed in previous sessions. And yeah, this is based on this paper we posted on archive. Um, and okay, as we have seen, let me, sorry. Okay. Yeah. As we have seen in the very nice introduction session part, that from the Hamiltonian perspective, the Yang-Lie problem is the same as just quantum Ising model in the presence of an imaginary magnetic field. And so what we are going to consider is this Hamiltonian of a bilayer system where we have this transverse field Nx, and we set the strength to 1 as our energy unit. And we have this ferromagnetic coupling tuned by the pseudopotential V. And we also add this imaginary longitudinal field that gives us the Yang-Lie transition. So that manifests the three symmetries, SO3 reflection, and most importantly, it has this PT symmetry, and this is the phase diagram. So when lambda is 0, this is the ordinary paramagnetic to ferromagnetic Ising transition, where we have this 2 plus 1D Ising criticality. And when V is 0, actually you hit the 0 plus 1D Yang-Lie criticality by tuning lambda. And the 2 plus 1D Yang-Lie should be this entire critical line that separates this PT symmetric phase to PT broken phase. And fortunately, this Yang-Lie CFT itself does not break PD symmetry. So we still have real scaling dimensions, and we should still see real eigenenergies, at least the low-lying part of it, the spectrum. And in order to use this Hamiltonian to tackle the Yang-Lie CFT, we basically have to answer the two questions that has been addressed in the introduction, which is how to find the critical point and how to do finite size scaling. And in the rest of the talk, I would at least provide our version of answer to these two questions. Okay. And so, yeah, first, how do you find the critical point? It essentially boils down to how you define a critical system in the finite size system, critical point in the finite size system. And here, because we have access to the energy spectrum and we have the state operator correspondence on the fuzzy sphere, so we would like to use the conformality of the energy spectrum as the definition of the critical point. So basically, if the system is at the critical point, then we expect the energy spectrum to show many integer level spacings. For example, if we just pick some typical point, parameter point, some typical pseudopotentials and the imaginary field in the PD symmetric phase, then this is the energy spectrum that we will see. And you can see and we would like to expect this guy to correspond to the phi, and this guy corresponds to the spin one descendant and so on. And we expect this guy, for example, to be the stress edge tensor. And so what we are going to do is we just do a gradient descent to search for parameters that produce this integer spacing. Okay, and how many states that you want to choose is you have to kind of test it in the numerics, and how many parameters you have to fine tune is also something that you have to test in the numerics. And in practice, we find it seems to be enough to just work with these five states. We just consider the conformal family of phi and the four of these descendants, and we also choose this state that corresponds to the stress edge tensor. And we fine-tune five parameters, which are the V0 to V3 pseudopotential and the longitudinal field. And we tune this parameter and see when, after rescaling, these few states are close to having a integer energy spacing. And that's our method. And this also has been used in this paper to search for some unknown CFTs. And and after this gradient descent, just with 8 electrons, and you will see this energy spectrum. So you can see that the energy of this guy goes down, and the rest of it also has integer spacings, which is what we are optimized for. But surprisingly, all the higher energy levels also tend to have a integer spacing. And we can also see this guy, it does not have integer spacing with this, so that probably is some new descendant, so new primaries, which probably is the phi cube. But before we're saying more about, we make more conclusions or like draw more conclusions from this spectrum, we should question ourselves that whether this is a true critical system, a genuine CFT, or it's just a result of overfitting. So we have to test. And our idea here, we follow the idea of this paper that a genuine CFT is not about a single critical point, but it should also dictate the finite size energy spectrums nearby. So basically, if the system is a CFT, then we tune it a little bit away from the critical point. We should be able to describe it, the Hamiltonian after rescaling by this effective description, where we have this HCFT plus the relevant perturbation and so on. And we should be able to use conformal perturbation to predict all the energy spectrums at the nearby points when the system is deviates a little bit away from the critical point. So what we are going to do following this paper is just we do the tree level or first order conformal perturbation to calculate how the presence of this relevant operator shifts energies at the of different states. So we have a state labeled by I, and delta I is the its value at the CFD point, and then we can compute this delta E using conformal perturbation. And this guy, of course, depends on some CFD data. For example, the scaling dimension of this guy, the scaling dimension of this relevant operator perturbation, and some OPE coefficient. And we want to see whether after rescaling, whether the numerically obtained energy after rescaling is the same as the prediction from the conformal perturbation calculation. Okay, so the gist of this idea is that we want to use a conformal perturbation to verify whether the parameter we get out of the gradient descent describes a genuine CFT or not. And in practice, we just try to match these three states, the energy of these four states, sorry, phi, partial phi, box phi, and T mu nu. The reason, okay, and then we need the two parameters actually. One is the scaling dimension delta phi itself, and another is this ratio of this OPE coefficient. So what we're going to do is that we tune our lambda. So we tune the lambda z a little bit, and given a lambda, we use our conformal perturbation to compute the energy, and then we also do exact diagonalization to get a set of a numerical result of the energy, and we can ask how to risk how to choose this alpha, this rescaling factor, and this coefficient g phi to match them, to reduce to minimize the deviation. And we want to ask what is the delta phi and r. We also want to ask what is the delta phi and r that can max and that can minimize the total deviation at all different nearby lambda z. Um, and this is the result that we get. You can see that the optimal delta phi is 0.19. That is pretty close to what you can directly read out from the spectrum. And this ratio of the OP coefficient is also it's consistent. Not exactly the same, but it's consistent with the direct calculation using the energy spectrum. And you can see that the effective coupling, it changes sign, and it's almost a zero um, at the critical point. That is output from the gradient descent calculation, and this rescaling factor, it barely changes across the putative critical point. Um, one side comment is that what states that you choose here. So this delta phi and r, if you choose different states and different windows for the lambda z to do this sanity check, you will get a slightly different answer for delta phi and r. So here I don't want to uh, at least my personal take is that this is just a sanity check of the result obtained from the direct calculation and shouldn't be viewed as a more reliable answer. Um, because what states you want to choose and what window you want to use here is kind of there's a lot of art in it. But anyway, so at least the parameter have passed this sanity check. So we are able to resolve the spectrum a little bit and try to say something more. And then this is the result that we can get for 8 electrons. So you can see that we can resolve this a conformal family or conformal multiplet for the phi primary and also the phi cube. And here it's the conformal family for stress energy tensor, and this one is the conformal family for the spin 4 primary. And also there seems to be additional conformal family for this PT odd spin 2 primary. We call it phi mu nu. And their scaling dimension and that you can extract with these 8 electrons is listed here. Okay. So let me summarize the workflow of what you want to do at a given system size. So first, you can do gradient descent to search for parameters that produces a maximal integer spacing. And second, you want to use some conformal perturbation to verify whether you get a genuine CFT. Because sometimes if you choose a wrong starting point to do the gradient descent, it's actually easy to get a fake parameter that gives you very nice integerally spaced spectrum, but it's actually not a CFT. And so you have to do some more work to rule that out, either conformal perturbation or just staring at the spectrum to rule it out. And then you can, after it passes some sanity check, you can use it to extract CFD data. So this is kind of different from finding critical point by finite size scaling. And the advantage is that it maximally utilizes the feature of the fuzzy sphere setup, which is the state operator correspondence and the very high tunability of the pseudo potentials. And this part is something that you don't naturally have when you study some lattice models, but it's just naturally there for the fuzzy sphere setup. So you can use that. And I guess most importantly, it allows you to say something meaningful without doing any finite size scaling. But the disadvantage is that the system size is just so small that you can clearly see the deviations at the high energy part of the spectrum. So now let's try to figure out how to increase the system size and minimize the finite size correction. And the conventional wisdom is just to fix the parameter because we already locate the critical point at the small system size, and we just fix the parameter and increase the system size. That's the first thing that you want to try. But unfortunately, if we just apply the same parameter that gives you this very nice conformal spectrum for 8 electrons to a larger system sizes, for example, just 9 electrons, you will immediately find that the system is already in the PD broken phase. So this is the new spectrum that you get with the same parameter, but at a slightly larger system size. And you can see that I only plot the real part. I didn't plot the imaginary part, but it's already in the PD broken phase. So So we can see that the location of the critical points, it drifts with the system size, which is the phenomenon that has been observed in other systems, but it causes like very severe problem uh, for the Yang CFT. So we have to we have to fix that. But before stating our resolution, let me revisit the 1 plus 1D Yang lattice model just as a better comparison between the two setups. Maybe it suggests something. So here is again the Hamiltonian for the 1 plus 1D Yang problem, and with this spectrum, sorry, with this phase diagram. And you still have to fine-tune the parameters, this lambda and v, to minimize finite size correction. And we find that tuning the transition along the diagonal line seems to give you invisible finite size effect, uh, which from the hindsight seems to make sense because it's very far from 0 plus 1D Yang and also very far from this 1 plus 1D Ising. Far just in the most naive sense. Um, and if you tune the transition along the diagonal line, and you can look at, for example, finite size scaling of dimensionless quantities, and here we look at the ratio of level spacing, and we can look at the first three energy levels, E2, E1, and E0, and we compute E2 minus E1 divided by E1 minus E0. And this dashed line is the CFT prediction. It's three halves. And if you compute it across different system sizes, they very nicely crosses at this CFT predictions point. And you can use that as your definition of a critical point. And this is the conformal tower energy spectrum, which collapse with the conformal tower nicely, at least in the low energy part. And you can even use it to compute OP coefficient, which of course will see corrections because the operator overlaps with the descendants, and that anyway gives you a finite size correction. But if you do a finite size scaling, it collapses to the CFT prediction very well. And then you want to do the same thing on the 2 plus 1D fuzzy sphere model, and then you run into a problem. For example, you compute the same quantity, ratio of level spacing, just by violation of unitarity bound, you know that this ratio at the true critical point should be larger than 2. But but you can see that these lines crosses first the line, the crossing point drifts a lot with the system size, and then the crossing point is around zero point 0.5, is much lower than 2. So if you use, and it's not surprising that if you use this approximate crossing point as your definition of a critical point, you will see that the spectrum is not close to being conformal at all. So so this drift is seems to be very significant for this 2 plus 1D Yang fuzzy sphere model. And so we have to understand that or uh, deal with that in order to do a good finite size scaling. And here the drift of this critical point on the fuzzy sphere might be just attributed to the ambiguity of the definition of pseudopotentials, which is something that has been observed in this very first paper uh, on the fuzzy sphere. So here uh, we call that in the Hamiltonian, we have this ferromagnetic coupling that is defined via the sphere pseudopotentials. And if we want to fix the pseudopotential in the real space, then its expansion as some summation of some delta functions or its derivatives. If we fix the definition of that in the real space, then its expansion in the angular momentum space, the coefficient can change and by amount 1 over r squared. And this ambiguity will eventually goes away in the thermodynamic limit, but it's there in the finite size sphere. And it's worth mentioning that there is no such kind of ambiguity on the plane or on a torus. And because of this ambiguity, when we try to relate this microscopic Hamiltonian to our effective description of the Hamiltonian written in this way. Then the effective coupling, the relation between the effective coupling and the microscopic parameters in the Hamiltonian should also suffer from this ambiguity. So instead of just writing G phi linearly related to lambda z or the pseudopotential V, it also has this term C phi divided by R squared, and similarly for this phi cube coupling. And and then it's it's kind of clear that the crossing point of this dimensionless quantity roughly corresponds to G phi at R is equal to G phi G at R equals to G at R plus delta R, like increase the system size a little bit. But actually the conformality or the system the finite the location where the finite size system is critical should correspond to G phi equals to G phi cube equals to zero. Um, okay, so that's why we may not want to use this crossing point as the definition of the critical point on the fuzzy sphere. And so we will use this as our definition. More specifically, what we want to do is the following. So we fix V1 to V3 obtained from the gradient descent with 8 electrons. And as we change the system size, increase the system size, we change lambda z and V0. We do this two parameter tuning to maximize the conformality of the energy spectrum. And if we work with these ansatz, that just means we have G phi and G phi cube both being tuned to zero, and of course we assume that the effect of higher irrelevant operators are not important here. And a side remark here is that this two parameter tuning seems to be necessary actually to make sure that the low energy part of the spectrum being real. Because sometimes if you don't do the two parameter tuning, what you will find is that some high energies states their energy will happens to go close, and because this is a non-Hermitian system, there's no natural level repulsion, and they will collapse and gives you imaginary part of the energy, and that's not very good. So we have to do this two parameter tuning to avoid that. And then if you follow this procedure, you'll find that the optimal V0 and lambda z at different system sizes, they follow this curve. It seems to fit very well with a linear fitting in 1 over n. So that's kind of confirming this ansatz. And if you do finite size scaling of this parameter, and these 2 points seems to be the lambda zc and vc, the critical point in the thermodynamic limit. And if you just use this vc and lambda c and vc, plug it in, and compute the energy gap and look at the finite size scaling of the energy gap, this is what you'll find. You'll see that the first gap, it doesn't asymptote to zero. But asymptotes to other values. And that actually makes sense because if you use VC and lambda C, um, the gap will get a correction from this phi term, and uh, you can include that effect and do improve the finite size scaling. And that is this orange curve, which does go to zero eventually. Okay, but that's logic of doing finite size scaling. And here is the improved result that we get with 12 electrons. And you can see that there's a less finite size correction at the even higher energies. And so we can so that seems to be a more reliable result than what we have seen for the result we obtained with 8 electrons. And using the same logic, we can do finite size scaling of some conformal data. So for example, if we monitor how the energy of the phi state changes as a function of system size. These are the green dots. It still has a shift. And here we want to attribute this shift to some unknown uh, some other unknown irrelevant operators, and we estimate that operator to have a um, scaling dimension 8. And that is because here I only plot the spectrum up to scaling dimension 7, but actually there are two states near 8, and they have a but unfortunately, their energies have a little bit imaginary part, so you cannot use them very reliably. But that's why we estimate there might be some new state near scalar dimension 8, and so we attribute this drift as the effect of that unknown irrelevant primary, and we estimate the scalar dimension to be 8, and use that to plot to get this orange curve. If you use a larger scalar dimension like a 9 or 10, this orange curve will bend down and give you, but but this is what we use here. And finally, we estimate the scalar dimension to be 0.29, which seems to be significantly larger than that has been obtained in other approaches or by other groups, by the other two groups. And we do the same thing for the other primaries and as well using the same method. And you can also do finite size scaling for the OP coefficient. And so this is the result. This is the plot for the 555 coefficient. And you can see that the answer is around 1.91 to 1.92. The two answers are obtained using either an X or NZ because both of them have overlap with phi, and you can use both to compute the OP coefficient, and that naturally gives you a estimate of error. And this solid line is just do the most naive linear fitting, just include um, the overlap, include the correction from the overlap between n and the next irrelevant operator. Sorry, the descendant of phi, and that's the solid line. It gives you a larger estimate, and you can do the same thing for other OP coefficient. And here is the just a table of result. Of course, you don't have to remember the numbers just to I just put the result there to give you a flavor uh, uh, of this answer of the answers we get. Okay, here's pretty much what I want to say, and here are some outlooks. First is we have seen this drift across different system sizes um, of the critical point, the drift of the critical point, and so we want to ask, is this just a feature of the fuzzy sphere regularization or intrinsic to critical systems on the sphere? I forgot to put a reference here, but in the recent paper posted um, by Andrew Loshley and Slava Rychkov, they attribute this to the coupling uh, between the CFT operators and the background curvature. But so it's questionable whether this is something intrinsic or a feature of the fuzzy sphere regularization itself. Um, and another question is, it's interesting to study the defect CFT, of course. And another direction is to probe the entanglement um, at the critical point. And one can also try to consider actually a 4 plus 1D Yang using the fuzzy sphere setup there. But yeah, that's pretty much what I want to say. Thank you for your attention.
Thanks very much, Ruha, for a very good talk. Very nice results. So if somebody wants to ask a question, you have to speak in the mic, but I'm going to pass you the mic. Yeah, there's a question there.
Hi, thank you for your very nice talk. I had a question about your OP coefficients. So in the fit that you showed in the very beginning, you're fitting to both states in the phi and the T family. So you're also optimizing over this ratio of C phi 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 and C phi TT. But presumably you're only showing the absolute value, but presumably the phase is also part of the conformal data. And presumably in your prediction from the fuzzy sphere, you should be able to get this phase. So I'm just wondering whether the sign of the ratio of OP coefficients also matches between what your fit produces and your fuzzy sphere results.
What phase?
So you define this ratio R in your fits, which is the absolute value of the ratio of OP coefficients. I think it was earlier in the talk.
Oh, this
Yes.
R.
Yes. I'm just wondering about the sign of the ratio of the OP coefficients without taking the absolute value.
Oh, I see.
Because when you compute these OP coefficients via matrix elements on the fuzzy sphere, presumably you get this sign when you take the ratio. You have a specific sign.
Uh, oh, I see. Yeah, thanks for the question. Yeah, sir, I don't spend too much time on, yeah, I don't look at this, sir. I don't know. Yeah. But when I compute the, to compute the OP coefficient, there seems, I recall that there is some ambiguity in defining the plus minus signs um, of the state itself. Let me think. Oh, actually, that doesn't. Oh, I see. Um,
They both flip sign based on your convention for phi, but the ratio should be
right.
well defined.
Right. Yeah. Sorry. I don't look at this. Yeah. I'll look at that. Yeah. Thanks for the comment. Yeah.
Okay. There are more questions.
Hi. So I was wondering about the drifting you see by finite-size scaling. So in a classical standard simulation, you can also see driftings like that on finite sizes, and you can also define pseudo-critical points and so on. But what you know from the underlying theory is how these drifts converge to the true critical point. They don't converge like 1 over L or something like that. They do converge with a power law, which is a critical exponent. So I was wondering if this is the case here, or if the fuzzy sphere is inducing some correction that go beyond the standard Banach scaling.
Uh, yeah. Thanks for the question. Um, right. Actually, if you uh maybe let's just say what I know here in this specific context. If you don't, for example, you just look at this 1D model and you don't tune the transition along the diagonal line. You tune it along some other line. You can also still you of course see drift. For example, you compute the ratio of this dimensionless quantity, you will see drift. Um, but my point here is that it seems that for this 1D model, you can tune the drift away with a little bit fine tuning. Um, but for this 2 plus 1D Yang-Lee model, and actually in another model that we have looked at with Zlatko and Christ, um, and with this one third the icing transition at the total one third filling, it seems that we cannot tune the drift away, and this drift is all seems always depends on linearly depends on 1 over n, and so that what makes us think that is something that's very unique to the uh, unique feature of the fuzzy sphere. Um, yeah.
Maybe it might not be unique because even in classical model you can see the things you are saying. So you tune one parameter along a line which should be the same universality class, and it might be that there is a special point where the leading irrelevant operator drops away from the action. Might or might be, you don't know a priori if this can happen. And if when this happens, of course, the crossing then don't drift anymore.
Oh, I
So
see.
might also be the case here.
I see. I see.
Okay, thank you.
Yeah, thanks for the comment.
About the previous point, I think the point here is that on the sphere there are more couplings than in flat space. So whatever difficulty you have at tuning drift away in flat space, on fuzzy sphere you will have more difficulties because there are extra couplings which involve curvature tensor. So you may be lucky or you may be less lucky, but it's going to be more difficult. It's not. I don't think it's a difference of it's not a difference of principle, but it might be difference of practice that you just have to work harder, and sometimes you may fail. I think that's the. But it's still controlled by RG. You don't have to invent a new language to speak about such things.
For this spin 4 primary multiplot, can you show the data again, please?
Yeah.
I would expect a spin 2 descendant at the second level. Why is there no spin 2 descendant?
Oh, you just cannot resolve it. I'm
You
not.
could just
Yeah. I should put a line there.
but you cannot resolve the state.
Yeah, I cannot resolve.
And another thing, the estimates from the resummed 6 minus epsilon expansion, they are not good enough to compare to this, or they're comparable for the dimension of phi, say.
So I missed what you said at the beginning of the
Just the
question.
epsilon expansion, the 6 minus epsilon expansion, when it's resummed, does it give an estimate that we can compare to for this 0.2 for phi or not?
Oh, yeah, I think I didn't put the result there. Let me recall. Uh, yeah, the epsilon expansion result is between 0.22 and 0.25, I think, for the phi, single dimension of phi. You're asking about the phi, right?
Yeah, one comment on the previous question and a question for Ruihua. Yeah, the epsilon expansion is
Speaking to the mic, otherwise he doesn't hear.
the epsilon expansion is super precise in the sense that, for instance, when you can compare with the exact results, like in 2D, it's like 1 or 2% precision. So I think we can trust the 3D as well then. But a question about the delta phi extrapolation that you are showing us here. I didn't understood the what you said about the fitting function. You were saying you are in the first plot of delta phi at large n. Do you hear me?
Yeah, I do.
Um, because you said you were adding an irrelevant operator of dimension 8. I understood that. Well, why aren't you adding phi cube and the spin 4 for the delta phi extrapolation?
Oh yeah, because thanks for the question. That's because we do this two parameter tuning and we
Right.
ass-
What about spin 4?
sorry.
Then what about the spin 4?
Um
I'm asking because we found it was important to include that. And that could change that's going to change for sure your extrapolation, and maybe you get then better agreement with the epsilon expansion if you include the spin 4.
I see.
Suggestion.
Oh, I see. Yeah.
It's higher up in the spectrum. Spin 2.
Okay, well, I let's thank again Ruihua for a very nice talk.